Well, welcome Earth Space Science students. This is the second attempt at this. I'm using Screencast-O-Matic for this recording, and it went bazzacko on me the first time. So here we go, trying again. So we're dealing today with chemistry and minerals, and this new environment we have at Bethel that won't last too long, hopefully. This is normally where I would have you do some rock candy to illustrate the crystallization process, which it is a very nice parallel. It works very well. It very nicely mimics what goes on in magma without having to endure 2,000 degrees Fahrenheit. In an elementary classroom, they run the gamut. Some districts don't allow heat in classrooms, others do. You'll just have to find out. We'll talk a little more about that probably another day. So today the topic, however, is chemistry and minerals, and if you're looking at your notes, you'll see a description there to begin with. It says an atom is the smallest fraction of an element that can exist and still show the characteristics of that element and is not divisible by chemical means. And I will never ask you to regurgitate that as part of a quiz or an exam. Okay? So why did I bring it up? Well, there's a couple of things that may be relevant. I hope are relevant. Let's look at still show the characteristics of that element part. So here I have a piece of what's called native copper. This is a piece of copper, just as it was found probably in northern Michigan. That's copper country. There's a lot of this up there. Okay, and this was formed as the copper was deposited in a vein, and this little nugget came out of that type of a deposit. So what is a characteristic of copper? Well, a characteristic of copper has to do with why we use it in things like wiring. It is a good conductor of electricity. So electricity conducting, is accomplished by electrons moving through the copper wire and conducting electricity. That's what is actually going on. So copper mineral has to have electrons that are easily movable, freely moving, and it does. Another thing we find with copper is it's commonly used in plumbing, like we see here. Now, some of that has to do with the fact that it's malleable or bendable, that it's easily solderable. We can solder two pieces together. But another feature of copper that's important why it's used in plumbing is that it has an antibiotic quality. Bacteria don't live well on it. All those would be characteristics of the mineral copper. Okay? And the smallest piece of it that can exist should do those things. So if we look then at an atom, if I asked you what an atom was, I'm guessing that quite likely an image like this might show up. You might think of something of that sort. And there's a couple of problems with this. It's a good image. I mean, here we have protons and electrons in the nucleus. We have protons and neutrons in the nucleus, electrons outside of the nucleus. The electrons are too big relative to the size of the protons and neutrons. In reality, that electron would be about 1,850th the size of these protons and neutrons. Another problem is that the electrons are too close to the nucleus. If we were to shrink this nucleus down to about the size of a gumball, something like that nucleus, and place it out behind second base in some baseball stadium like Target Field, for instance, these electrons would be specks of dust whipping around the nosebleed seats, way out there in the cheap seats. So this is important to recognize that there's a lot more space between electrons and nucleus than this image might lead you to believe. Now that's going to be important for geology, but probably more important for astronomy when we get there. But since we're talking about atoms here, I thought I would bring that up. So we're talking mainly about protons, neutrons, and electrons, but it's important to realize there are other subatomic particles, positrons, neutrons, or positrons, muons, taus, neutrinos, quarks. All of those are other types of subatomic particles, but we're not going to be dealing with them too much. We're just looking at that subset of chemistry that's going to be important to geology. So in your notes, it starts off with a proton. Proton has a weight of 1 and a plus charge. It is positively charged. A neutron has a weight of 1 and has no charge. You might say, 1 what? Well, the 1 is an atomic mass unit. It's actually 1/12 the weight of a carbon atom is another way to look at it. Basically, these subatomic particles have a weight, but this is a gram. Okay, I wish you could heft it, so it's not real heavy. But this is just to give you size comparison. This is 1 gram. That carbon atom, that proton or that neutron, I should say, has a weight, and if we were to measure that in grams, it would be such an incredibly small number that it'd be difficult to deal with that. So chemists decided, hey, we'll come up with a new unit of measurement. It'll be the atomic mass unit. It's basically the weight of 1 proton or 1 neutron, okay? And as I mentioned, an electron is 1/1850th the size of a proton or a neutron. So they're much smaller. But electrons might be much smaller, but they pack a potent wallop. So even though this little structure here is not in actuality the same size, if this were the proton, as this proton, it would be much, much smaller. They would have the same charge, but in opposite direction. So the proton would be positively charged. The electron would be negatively charged. They would have the same level of charge, if you will, despite the size difference in the structure, but in the opposite direction. So a proton, positive charge, electron, negative charge. And if there are two are together, they would cancel each other out. That's how closely matched they are, even though this electron is so much smaller physically than the proton. Okay, so proton weight of 1 atomic mass unit and a plus charge. Neutron weight of 1 atomic mass unit, no charge. Electron, very little weight, but a strong negative charge. If you remember from chemistry, there were probably associations made, like atoms or elements. Elements are atoms with different arrangements of protons and electrons and neutrons. They join together to form molecules, and then it might have gone, molecules are joined together to find compounds and so on and so forth. If you're a biologist, you might say cells and structures and systems. But to a geologist, the atoms or elements are joined together to form molecules, but then those molecules are joined together to form minerals, and the minerals are joined together to form rocks. The important point here is rocks are made of minerals, are made of accumulations of minerals. Okay, so let's look at this a little more detail and just think about the parts of it that are going to be important for us as geologists, thinking about how this structure works. We've already talked about the concept of isotopes. And isotopes are atoms with an unusual number of neutrons. So if I go down here, I'm going to pull up another page, another site, and I want the periodic table. Okay, there we go. Actually, I wonder if I got the one I want on the bottom of this page here. Yeah, there's the one I want. So if you look at the periodic table, now this can cause some of you to shudder and break into cold sweats, and others it's familiar ground. But when we're looking at isotopes, we're looking at these atoms in this chart here. Since we talked about carbon, let's look at carbon. In fact, let's zoom in on it just a little bit. Ooh, if I can. Oops, I got to do this, okay. Nope, I can't. Well, yes I can. We'll try that. A little better. Okay, so here's carbon. And the way you can read this in this periodic table, and there are different arrangements of them. This number right here is the atomic number, and that is the number of protons that most carbon atoms have, that all carbon atoms have. This number underneath it is the atomic mass. That's the number of protons plus the number of neutrons. And the reason it's a decimal is because, as we've noted earlier, almost all the carbons in all the world have 6 protons and 6 neutrons. That makes them carbon-12. 6 plus 6 is 12. But if you have an additional neutron, that makes it 6 protons, 7 neutrons. That makes carbon-13, but that's a stable, what we would call an isotope. The isotope that we talked about before is carbon-14, which has 6 protons and 8 neutrons. And that is an unstable isotope that breaks down very uniformly over time into nitrogen-14. And we use the example of determining the age of something based on the ratio of carbon-14 in it to nitrogen-14. So when we talked about that before, we were talking about an isotope of carbon, an atom of carbon with an unusual number of neutrons. Okay, so that's an isotope, not an unfamiliar term. The other thing that I wanted to point out with this periodic table is that you see no plus or minus around the carbon here. And if you see no plus or minus around the C, then and you see the 6 here, which tells you the number of protons, then it is okay for you to assume, since there is no plus or minus, that it has the same number of electrons. So if we go back to this image here, these, I said, I think I pointed to this before and just as an off-the-cuff remark, referred to it as a proton. But in this diagram, it might be better to think of the red dots as the protons and the blue dots as the neutrons. Doesn't matter a lot. But it doesn't have a plus or minus by it, and there's the same number of protons as there are electrons, so it would have no charge. Similarly here, this carbon, there's no plus or minus by it, so it's okay to assume that that 6 tells you the number of protons. It is also the number of electrons. Okay. Now, protons and neutrons, as I said, are found in the nucleus. The electrons orbit the nucleus. Now, I shouldn't say orbit, that gets chemists angry. Circles the nucleus in shells made up of different energy levels. Now, this is problematic because this has 3 here, and that would make chemists angry too. This is a better model of an atom, okay? And so in this atom, this first shell has 2 electrons in it, and that's common. Now, this is for the small atoms that we're going to be dealing with in geology. And we're not worried about s orbitals and p orbitals and things like that if you remember your organic chemistry. We're not going there. So the next shell out has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. Same for the last one. And these atoms that we're interested in, these shells, the atom likes to have 8 electrons in them. And if it does, it's a fulfilled atom. It's very happy and comfortable and everything like that. So this is a normal arrangement. 2, 8, and 8 of the small atoms that we're dealing with. Okay, if we go back to this diagram, we see that there's not many atoms that actually are set up that way. Only these over on the right side. Helium here, you see a 2, which it is no plus or minus by the He, so you can assume 2 electrons. If we've got 2 protons and 2 electrons, we have no net charge. And so with 2 electrons, there would be 2 in the first shell, and we would have a happy, fulfilled atom. Neon, 2 plus 8 in the second shell gets us 10. We don't have a charge. Argon, 2 in the first, 8 in the second gets us to 10. 8 in the third gets us to 18. No charge. Krypton, xenon, radon, I don't know on. All the rest of those atoms would be what we call non-reactive, inert. They're not going to react because they have a filled outer shell. They're happy. They don't need nothing, double negative, from any other atom. And there we go. Okay. But most other atoms here, like the carbon we talked about, may not be in that situation all the time. So with carbon, we have 2 in the first shell. That leaves us 4 for that second shell. So if we go back to here, that would not be what a carbon atom looks like. We would have 2 here, only 4 in this second shell. There would not be a third shell, and there would be 4 missing from the second shell. That is not a happy atom. It would be looking to bond, to get electrons from another atom, or at least share them. Okay, now in this diagram right here, this outer shell would be called a valence shell because these electrons are higher energy and they're not as tightly held to the nucleus. These are lower energy electrons here, and the nucleus holds them tightly. So these outer electrons are the ones that the atom might well lose, or it might share with another atom, and that's where we're going next. So we have this basic arrangement of an atom with the protons and neutrons here, electrons out here. The idea that there are 2 electrons in the first shell, and that the atoms that we're interested in like to have 8 in the second shell, and we'll move on from that. Okay. Now when we talked about the Earth, and we talked about it like it was an ogre, and we were going from outer space, and we defined that a number of different ways, but we were talking about the layers, and one of the layers was the ionosphere. Okay, and so in the ionosphere there are lots of, as you might guess it, ions. If we go back to the periodic table here, let's pick on oxygen right here. Oxygen has 8 protons. I see no plus or minus, so we can assume 8 electrons. 2 in the first shell, 6 in the second. Okay, it does not have a filled outer shell, it is not a happy electron, a happy atom, I should say. Give me one quick second here, folks. I need to refresh the screen. Okay, so atoms without a filled outer shell might well gain or lose an electron, and when they have more electrons than protons, they would have a negative charge. If they have less electrons than protons, they would have a net positive charge. Because there's more protons than electrons, it gives you a positive charge. Okay? So keeping that in mind, we're going to look at bonds then next. And there are 3 kinds of bonds, and I'm guessing you would have thought of 2 of them. Ionic and covalent would be the first ones. And I just want to look here, see, I'm just kind of processing this as I go, and thinking about images that I want, and I don't see the one that I'm looking for, so I might pull up a different one here. The first atom we're going to look at is, or this first molecule, is sodium chloride, more commonly known as table salt. Okay, so if we look at images of sodium chloride, yeah, pretty common images come to mind. And so if you look at how the sodium and the chloride then are portrayed in this model right here, well, that's a pretty good model. Let's go back to our periodic table and see if we can learn something about sodium and chloride. Okay, so first over here is sodium, Na. The Na stands for natrium. That's the Latin for sodium. That's why it has the Na there. So sodium has 11 protons. That's what that number means right here. No plus or minus, so we assume 11 electrons. It would have 2 in the first shell, and that would leave 8 in the second shell, and 1 in a third shell. Okay, so that leaves 1 electron in that outer shell for sodium, and it's not going to like that a whole lot, because you know it wants to have 8. It's only got 1. That's not going to work so good. So what's it going to do? So we need to go back then to chloride right here, and let's find chloride right here over here. Again, Cl, no plus or minus. So 17 protons, so assume the 17 electrons. 2 in the first shell, leaves us 15 left. 8 in the second shell. Okay, that's a total of 10, so we have 7 left. Leaves 7 in the outer shell. So what that means is that it's looking for 1 to fill the outer shell. Sodium has only 1 in its outer shell. So sodium very gladly contributes its 1 electron in its outer shell to chloride. When it does that, it turns it into chlorine. And now let's think about what's just happened. If sodium has basically lost, it's given its electron to the chloride atom, it now has 1 more proton in the nucleus than it has electrons in the shell around it, the orbitals around it. So that means there's 1 additional proton, so it's going to have a net plus charge, plus 1. The chloride, on the other hand, it has gained an electron. Now it has 1 more. It has 18 electrons and only 17 protons, so it's going to have a negative charge. And just like people, opposites attract. The negatively charged chloride will be attracted to the now positively charged sodium, and we have sodium chloride. And that's what all these illustrations are trying to show. Sodium chloride bonded together in a cube, and that's common. Let's see if I can click off of this, get a better look here. This is a cube of chloride. This is sodium chloride. This is how it might occur in nature. Of course, table salt, if you look at these little grains of salt on in there, they're little cubes. This is the mineral form of it, the larger mineral form. Of course, we call that halite. And I think, yeah, I don't know if somebody licked to that or not, but you can confirm it's halite pretty easily. Okay, so that's an ionic bond, because when sodium and chloride, when sodium loses an electron, becomes a positively charged ion. When chloride gains that electron, it becomes a negatively charged ion, and the two attract ionically and form halite. The next one, covalent bond. In this situation, the electrons don't permanently leave one nucleus and move to another nucleus like with sodium and chloride. No, in this case, the electrons spend part of their time around one nucleus and part of their time around another nucleus. They are truly shared. And that's what your notes say. And the good example is diamond, carbon-carbon bonds. Now, if we look at carbon, hopefully that'll make sense. So here we have carbon, and it has 6 protons, 2 in the first shell, 4 in the second. Okay, but when you look at that, 4, what does it do? There's not an easy solution like sodium and chloride. It's halfway to 8. So rather than give up electrons or steal electrons, it shares electrons with a neighboring atom. And is this the one I wanted? No, where'd you go? Here we go. That's not what I wanted either. Oh, sorry folks, looking at the wrong image. So with diamonds, what happens? Well, here's one diamond nucleus, and these lines here represent a shared electron, okay? And so this carbon atom right here, it wants 4 additional electrons. Well, it can't get them, so it shares one with this atom, one with this carbon atom, one with this carbon atom, and one with this carbon atom. Since it's around the nucleus some of the time, it's happy. And then here with here, and here with here, and so on and so forth, and you get a complex 3-dimensional look at diamond. And it's kind of fun when you think of diamond. You know, you think of that clear look. And this is a model of the largest diamond ever found, the Cullinan diamond. I think it was found in 1912 in South Africa. And it was cut into this number of smaller diamonds plus chips. And just to show you what this one looks like in reality, Queen Elizabeth is wearing it in this picture here. There it is right there. That diamond, that original diamond, weighed 1.5 pounds, if you can imagine that. Now, diamonds are set in gold, typically, and so we think of them as heavy, but in reality, it's the gold setting that's heavy, not the diamonds. And we measure diamonds in carats, but that's why I had this image up here. That can be kind of problematic. If I can get to that image. Maybe I can't get to that image. There we go. Come on. I'm in the way. There, get out of the way, me. You know, all these different sized carats. Well, a diamond is not measured as in comparison to a carat. It's measured in comparison to a carob seed. So here's the Hope diamond. It's blue colored. That's kind of strange for diamonds. This is a carob tree. These are carob pods. It's kind of like our locust. And here's a hand. This is a carob seed, and this is what they look like in a person's hand. So the ancient Egyptians actually started out with this measurement, and they took the average weight of a carob seed, and that's 1 carat weight. The way you get these different colored diamonds is by looking at this matrix here, and you would keep needing more and more carbon atoms around the edge of this to make all these atoms happy, and that would go on forever, but it doesn't. There's other atoms like boron or titanium that can fill out that matrix and make different colored diamonds. That's why you have pink diamonds, blue diamonds, yellow diamonds. Red diamonds, I think, are created when you irradiate them, but this clear diamond is one of the most common form of it. If you take those same carbon atoms and you arrange them differently like it's done here, see, because sometimes you can make a double bond, 2 carbon atoms will share 2 electrons, you can get another mineral that you may be writing with. That's this. I'll take these away so you can see this hopefully a little bit better. That's like this mineral right here. This is graphite. And we refer to our pencil leads as leads, but it's actually not lead, it's graphite. And the reason is the carbons are arranged in these thin little sheets that slide over one another very easily and write. Graphite actually feels smooth. It's actually a lubricant. It actually is a dry lubricant that you can put on metal parts, particularly in cold areas, and it does a good job of lubricating. Okay, lastly is the metallic bond. And metallic bond, that's what I talked about initially when I held up this piece of wire, and why copper is a good conductor of electricity. You'll see with metallic bonds, the outer electrons in those outer shells are relatively free to move through the whole mass of copper. This whole piece of copper, the electrons are moving all through it. And that's characteristic of a metallic bond, and that's what makes it a good conductor of electricity, that freedom to move of the electrons. All right, states of matter: solid, liquid, gas, plasma. The important piece here is to think about, if you've got, for most things that we're familiar with, a piece of material like this piece of copper, this is a solid. And in a solid, the atoms that make this up are packed tightly together. If I were to heat this up to the point that I could turn it into a liquid, the atoms would be less tightly packed together and free to move, and the volume would then increase. If I were to be able to convert this copper to a gas, well, then the atoms are even less tightly packed together, and the volume would increase again, in a plasma even more so. Plasma is a little bit different. Maximum movement of atoms or parts of atoms in the case of plasma, actually. To make the case that the volume of a material increases as you go from a solid to a liquid, and increases again as you go from a liquid to a gas, I've got a YouTube video here of a Russian gentleman that's going to put a little dry ice in some boiling water. And I'm probably going to not do this. I'm probably going to just include a link, because YouTube will flag this if I try to just show it on here and then publish this. So the point that so you can pause right here. I'll include the link on Moodle. And the point that I want you to notice is when the gentleman puts the dry ice in the boiling water, you can see how much dry ice he's putting in there, but then look at the amount of vapor that's coming off of there. It's a big increase in the amount of vapor, and it makes the point that as the state of matter changes from a solid to a liquid to a gas, the atoms become less densely packed and more movable. And you know that things that are less dense oftentimes are hotter and will rise. Now, there's a big exception to this, very important exception to this, that your kids are going to come into class maybe knowing something about, and that is water. What does water do when it freezes? Well, it's going from a liquid to a solid. What happens to its volume when it goes from a liquid to a solid? Well, it's the exception to the rule, folks. It expands in volume. Ugh, how inconvenient. Well, the deal is that with water, let's see if I can pull up quick. I didn't have this already pulled up for you, so that's my bad. Let's see, how should I do this? Try water molecules in ice and see if we get a good image. Yeah. Okay. So this is a really good image. Sometimes you get lucky. Oh, that won't open that way. Okay, that'll just be dark if I open that one. So I'm just going to slide this over and we'll use it like it is. Okay, so oops, I got to move me back down a little bit. There we go. So here we have ice. Here we have water. Here we have steam. You can see water. This is the liquid version of H2O. So here's one O and here's two H's. Okay, and really. This hydrogen should be attracted to this oxygen. We call it a hydrogen bond that attracts those molecules together. This is a covalent bond that holds the oxygen to the hydrogen, and that means that there's an electron that's shared. Because that electron spends more time circling this big oxygen and less time going around this little hydrogen, it spends more of its time around the oxygen. The electron is here more. That means this end of the molecule has a negative charge, little bit of a negative charge, because that's where the electron is more. This end of the molecule, the hydrogen end, has a net positive charge because that shared electron is there less often. So between this positive hydrogen and this negative oxygen, then there's a bond that forms, and we would call that a hydrogen bond. And that's illustrated very nicely here. The deal is, and this is why water is the exception, here we're going from a liquid to a solid. Everything else in the world, the volume should decrease when you go from a liquid to a solid. It doesn't with water because the length of this hydrogen bond actually increases when you go from a liquid to a solid. But you got to remember, everything else, virtually everything else, this volume would be less than this volume when it went from a liquid to a solid. Okay? So hopefully that's something that you can explain to your kids using this concept of the distribution of atoms in a solid, a liquid, a gas, and a plasma. Okay, I'm guessing some of you buy organic produce. And what are you getting when you buy something organic? Organic simply means it contains carbon. And so when you buy something that contains carbon, we call it organic. Well, oftentimes we're referring to organic produce as not having had Miracle-Gro used to raise it. This is an inorganic fertilizer. Okay, right here, these are inorganic fertilizers. If you were to buy something organic, it would have been fertilized with that. Okay, that's organic fertilizer, whatever came out of the south end of a north-facing cow. And we're similarly going with this concept because organic, we're simply defining as contains carbon. Inorganic does not contain carbon. Okay, mineral. Last bit of notes. A naturally occurring inorganic solid with a specific chemical structure and physical properties. Again, I won't ask you any of that on a quiz or an exam. But the physical properties are what we would look at to identify minerals. I'm not sure how that's going to function in a virtual environment, but that's where we would focus if we did have a face-to-face class, if we will have one. So here's some standalone points. Minerals are always electrically neutral. A mineral can be composed of a single type of element, but usually contain two or more. Okay, that's all straightforward. Most of Earth's crust is made of just 8 elements, 98%. If you took Earth's crust, that hard outer layer of Earth, and you broke it up into the elements, you know, that we find on the periodic table, you would find oxygen, silicon, aluminum, iron, calcium, magnesium, potassium, and sodium as making up almost all of Earth's crust. Of that, 84% of the crust is made up of just silicon and oxygen. Wow. So if we go back to that periodic table, if I can. So silicon, oxygen, big deals. Okay, that's a big part of Earth's crust. If we look at just minerals with silicon and oxygen in them, we would call them silicate minerals, and we're going to want to pay some attention to them. We find in nature that silicon and oxygen tend to arrange in specific ways. Now, this may be a little bit counterintuitive, but if you look here, silicon has 14 protons, and oxygen only has 8 protons. So you would assume maybe that the silicon would be larger. In reality, that's not the case. Oxygen, this is a representation of the relative size of those two. So the oxygen would be larger and the silicon would be smaller in the middle. Now, in nature, silicon and oxygen tend to arrange in this type of a pattern, with 4 oxygens around a central silicon, making sort of a pyramid-shaped structure. Okay, and so we would look at how this we call the silicon-oxygen tetrahedron, how that, you know, correlates to other types of minerals that we'll look at. Okay, so here we see standalone silicate tetrahedron. They're just by themselves, and sometimes though they bind together to form these single chains, and sometimes they form double chains. Sometimes they form sheets of mineral, and sometimes they form like a diamond, a 3-dimensional network that you just can't show in a 2-dimensional image. So the arrangement of those silicon-oxygen tetrahedron is going to make for the different minerals that, if we get a chance to, I will show you in lab. And then, of course, we have important non-silicate minerals like this halite right here. And this doesn't have silicon and oxygen in it. It has sodium and chloride. Well, folks, this lecture is woefully lacking without having the ability to show you the minerals that I'm talking about and be able to pass them around and have you identify them. But we'll stop at that, And I'll post this along with the link to the video that I referenced, and we will move on to something else the next time. We'll see what next week has to bring us. And look for David Soltero to bring you the Thursday class, and I look forward to what he has. He's been thinking a lot about it, working a lot on it, so give him your attention, ask good questions. Please, if you would do that, that would be great. And I'll see you hopefully next week.